I'm not tagging you. I was actually going to reflect on the fact that my mother would say the exact same thing. I'm a busy guy. I got a lot going on. Oh my God, look at that handsome devil. That's disturbing. Get out of here. I don't know. What do I look like? Am I going? Okay, I am. Okay. Oh, all right. So today we are going to take what we've been doing, which is quantitative chemistry, and we're going to apply it to reactions, to our previous unit. So here we have a very simple reaction. What kind of reaction is this? Sorry? I gotta be honest, I didn't hear a word anyone just said. Could somebody say it with like a bit of vim and vigor here, please? Oh, yeah, it is. Good. Okay. So it's a decomposition reaction. I heard that. Was that for me again? No. Okay. All right. I kind of feel like it's one of these things. Like, shut up, Orlando. Was that aimed at me? No, of course not. Shut up, Joseph Dylan Orlando, who lives in St. Catharines. Is that it? Oh, no, absolutely not. No, talking about different Joseph Dylan Orlando from St. Catharines. Anyway, it's a decomposition reaction, and I've put these lines in front of each thing because, of course, when we first look at this reaction, what do we notice? Yeah, that's right. Exactly. It's not balanced. What would I have to do to balance it? Again, I got to be honest. Pretend, hypothetically speaking, that your teacher's old and has been to a lot of rock concerts, all right? And like just his ears don't work like they used to. You're going to have to help me out here, all right? So sorry, what did you say? Okay, yeah. Because if we do this, right, the 2 there will let the oxygens balance, right? But then once we've done that, that means we have 4 hydrogens. So now we have 4 hydrogens and we're good. Yeah, very good. Okay. So a pretty simple balancing question, right? And then not that we even need it, but I'm going to put the 1 there just because I put a line there. So I feel like I should put something in it. Okay. What does that reaction actually tell me? Sorry? Yeah, but in terms of like just describe this reaction in words. What happens? Yes, ma'am. Yeah, so tell me how many of each. Like, tell me what this reaction tells me.
Okay. Do you want me to say the whole reaction or like left side, right side?
Whatever, however you want.
Okay, on the left side there's 4 hydrogens and 2 oxygens, and then on the right side there is 4 hydrogens and 2 oxygens.
Sure, great. So that tells us the law of conservation of mass is followed, right? Because all the atoms we start with, we're ending up with no mass is created, no mass is destroyed. If we weighed all the reactants, it'd weigh the same as all the products, all those things. Absolutely. The other thing it tells us is that if we take 2 water molecules and we react them together in a certain way, in this case, we need to give it quite a bit of energy. We've done it with electrical energy, electrolysis of water. If you take 2 water molecules and you bash them into each other in the right way, what can you get to happen? Yeah, and what do we get specifically? You're totally right. What specifically do we get as the products? They'll break apart, and they'll break apart into hydrogen. How many of those do we get? 2. And, right, 4 atoms, but 2 hydrogen molecules. You're right, absolutely 4 atoms, but 2 molecules, right? Because they come in pairs. They're diatomic, right? And we'll also get a diatomic oxygen. How many of those? 2 atoms. I was really trying to throw you a bone there, Karthik. Yeah, there we go. So, that's what the reaction tells us. It tells us a specific thing. Here's what I want to note. It tells us that 2 water molecules can react to yield 2 hydrogen molecules and 1 oxygen molecule. Now, again, can we go count out 2 water molecules? Is that something we can do? If I told you to go in the back and get me 2 water molecules, could you do that? Of course not. Why not? They're tiny. They're way too small. Absolutely. But the chemistry, the math tells us that this should be the reaction. Now, could you count out 20 water molecules? Nah, still too small. But if you counted out 20 water molecules and bashed them all together, what would it yield you? If instead of 2 water molecules, you had 20. How much hydrogen could you get? 20 molecules. How many oxygens could you get? What if you had 200 water molecules? 100 what? And 200 hydrogen. Good. That makes sense. What about 2 million? If we had 2 million hydrogen, or 2 million water rather, how many hydrogens would we get? And how many oxygens? 1 million. Great. Do we get the premise? It's like baking, right? This is the recipe to break down 2 water molecules. But if you want to double the recipe, you just double everything, right? If you're baking, if you have a recipe to make 4 cookies, but you want to make 40 cookies, what do you do to all the numbers in the recipe? For 40, 4 to 40. You'd multiply them all by? Yeah, right? And you can do whatever you want. You can double a recipe, you can triple a recipe, you can make a recipe 10 times bigger, you can make it 100 times bigger. The limit is just how many ingredients you can buy, right? Now, we said the issue with a recipe like this is that you can't count out 2 water molecules. But we just learned in the last couple of days, you actually can count out 6.02 times 10 to the 23rd water molecules. Because that magical number, 6.02 times 10 to the 23rd water molecules, we call not 1 gram, 1 mole. And 1 mole of water would weigh, well, we could work it out really quickly, right? 16 for the oxygen, 2 for the 2 hydrogens, 18 grams. So if you went and weighed out 18 grams of that, you would have a mole. But if we started with a mole of water, how much hydrogen would we expect to get? Well, the recipe says those numbers are the same, right? So we'd get a mole of hydrogen. And then how much oxygen would we get? Well, the recipe says we only get 1 oxygen for every 2 of those, so half as much. So we'd get half a mole. Well, how much does half a mole of oxygen weigh? Well, you could work it out. You'd say O2 is 16 plus 16 is 32. Half a mole of that should weigh 16. Does that make sense? With moles, you can take this recipe that's all about counting, and you can turn it into masses. And that you can go do in the back with a scale with some pretty basic equipment. And that's the power of today's lesson. We call that stoichiometry. So from this, I just really quickly want to show that this reaction, it tells us about individual atoms, but it also means that we could say that for every 2 moles of water, we should expect to get how much hydrogen? 2 moles of hydrogen. What's another ratio we could take from this? What else? No, 2 to 4 doesn't work. This reaction tells us that 2 to 2. We've already done that one, though. What about this ratio? How much oxygen do we expect to get? Great, so we could write that way, 1 mole of oxygen. If we wanted to, we could write it the other way. We could say for every 1 mole of oxygen, we should expect to get 2 moles of water. That's the same thing, but it's written differently. We could say for every 2 moles of hydrogen, we expect to get how much oxygen? How many moles? 1. The point I want to take from this is we can read this equation, and even though this equation is written to describe individual atoms, from it, we can conclude what we call the stoichiometric ratios, which basically says for every 2 waters, we want 2 hydrogens, or for every 2 waters, we'll expect to get 1 oxygen, or for every 2 hydrogens, we expect 1 oxygen. But here's the thing. We don't have to work with individual atoms. If that ratio is true for individual atoms, then that ratio is also true for moles of atoms, because a mole is just a counting, right? In other words, if a recipe called for 1 egg and 1 gram of sugar and 1 cup of milk, if you wanted to use a dozen eggs, you could also use a dozen grams of sugar and a dozen cups of milk. Do you know what I mean? And the recipe's going to work, because a dozen is just another counting number. Does that feel okay? Any recipe in the world if you put dozen after the number, the recipe will be the exact same recipe. It'll just be 12 times bigger. And if you put score after the number, the recipe will be the exact same recipe. It'll just be 20 times bigger. Does that make sense? So if you put mole after all the numbers here, the recipe will be the exact same recipe. It'll just be 6.02 times 10 to the 23rd times bigger, a lot bigger, which means it will take it from the atomic scale, which we can't work at. We can't move individual atoms, and it'll take it up to the human scale, where we can go in the back, put something on the balance, weigh it out, and do chemistry. How's that feel? Is that kind of okay? And then these fractions, I just want to show that since we're always working with fractions in dimensional analysis, do you see how we created fractions by looking at the equation? I said 2 moles of hydrogen in this reaction is equivalent to 2 moles of water, right? Or we could look at the same reaction and we could say, well, 2 moles of water is equivalent to 1 mole of oxygen. We can create a fraction by comparing any 2 things in the recipe. And it doesn't matter which 2 things you compare, and it doesn't matter which one you put on the top or the bottom. The ratio is still true. These are called the stoichiometric ratios, because today's lesson is all about the principle in chemistry that says that if you double a recipe, you use twice as much of everything, and you get twice as much of everything, and that principle is called stoichiometry. Stoichiometry. It's a stupid word. I don't know. I didn't invent it. Talk to, let's say, Calford. A lot of people don't know that, but Calford invented this word, and I blame him for it. Okay. This actually gets easier if you just do it. Does that make sense? It actually gets easier if you just do it. So let's just do it. Let's imagine that we're doing this reaction, which I'm just going to rewrite here so I have it above the question or below the question. We said that 2 water molecules can be induced to break down into 2 hydrogen gas molecules and 1 oxygen gas molecule. Okay, that's our reaction. And it's important to have a balanced chemical equation. You always need that. You can't do stoichiometry without a balanced chemical equation. It's like you can't bake precise baked goods without a recipe. You can cook without a recipe. I like to cook. You can cook without a recipe, you get good results. You try to free solo baking and just make it up as you go along, boy, you get crappy results. Bless you. Chemistry is more like baking than like cooking. Bless you again. So, the first thing you're going to need to do with any question like this is you need a balanced chemical equation. And then 2, let's just see what the question wants to know. And in this case, we know how many moles of water we're starting with, right? So I'm going to write that here, that we know how many moles of water. And it wants us to tell us then what? What's the question asking? Ask us, sorry. Yeah, what's the question asking us? I like to kind of make little roadmaps sometimes of like, what am I actually trying to figure out here? And in this case, what I'm trying to figure out is that I know that I have 2.3 times 10 to the negative 3 moles of water, right? But what I actually want to figure out is how many moles of hydrogen gas. Does that make sense? I think it's sometimes made more difficult to answer a question just because we don't actually kind of look and see that. So I want to know how many moles of hydrogen I'll get given a certain amount of water to start with. And then 3, just do dimensional analysis. This is going to be the answer to almost every question in chemistry this year. Very few formulas, very few times where I'm going to say, okay, rearrange this equation and solve for Q or whatever. Just do dimensional analysis. So we're going to start with what we know. What we know is that we have 2.3 times 10 to the negative 3 moles of what's given to us again? H2O, water, good. And then dimensional analysis tells us that we don't want to think about the numbers yet or anything like that. We just want to make a fraction and we want to think about units. What unit don't I want to talk about here? Moles of water. Where am I going to put that? At the bottom. That's a math trick. It just means that if we divide something by itself, it's going to go away. We won't be talking about moles of water anymore. What do I want to talk about? Moles of hydrogen gas. We're going to put that on the top. This is also a math trick. If I multiply by that unit, now that's going to be the unit of the solution we get here. But now I have to put numbers in here that are true. And where do we look for the relationship between moles of one thing and moles of something else? The recipe. And in chemistry, what's the recipe? The balanced chemical equation. So from the balanced chemical equation, we can say, okay, I start with 2.3 times 10 to the negative 3 moles of water, and according to the recipe, how much water do I use? The recipe says, well, for every 2 moles of water, I should expect to get how much hydrogen? 2 moles of hydrogen. Now, spoiler alert, is this going to be a very exciting answer? No. In fact, 2.3 times 2 is 4.6. Divided by 2 is 2.3. So the answer is 2.3 times 10 to the negative 3 moles of, but not water now, moles of hydrogen. Now, a question this easy, we actually wouldn't probably do this math for. In other words, if we just looked at this equation, looking at the equation should have told us that however much water we start with, that's how much hydrogen we can get, right? So if I started with 2, then I get, if I started with 3, I'd get, if I started with 11, I'd get, if I started with 2.3 times 10 to the negative 3, I would end with, yeah. So in this case, we probably didn't have to do the math, but do we see the process? Yeah. Sorry? Where'd I get it? From the question. The question where it said, when 2.3 times 10 to the negative 3 moles of water is decomposed. So yeah, no, that's okay. So that's not something you could have figured out. That's just what I asked you. In other words, it would be the equivalent if I went back into the lab and said, okay, we're going to do some chemistry here. I need you to start with 2.3 times 10 to the negative 3 moles of water. And we gave that to you in a little test tube. And I said, okay, before we go, how much hydrogen are you going to get? There's nothing magical about this number. I made it up. I just picked a random number. Does that make sense? Cool. Yeah. Good question. You always have to start with a balanced chemical equation. And so in this case, I actually gave it to you up here. We just rewrote it. But in a question where I didn't give you a balanced chemical equation, you'd have to make one. But the good thing is that's what our unit 2 is all about, right? But very good question. You have to always start with a chemical equation, and it always has to be balanced. You can't do meaningful chemistry with an unbalanced equation. Did that answer your question? It was a good question. You guys are full of good questions today. Every day, actually. I gotta say, you're a class of good questions, which is not always true. Yeah. I've got to be honest, I'm not hearing a word you're saying. Can we try again? Sorry. Yep, you can pick any number you wanted. So again, I just made up a random number, and I thought I'd throw some scientific notation at you to make sure we don't forget how to do that. And of course, this is pedantic, but just to make sure, how many sig figs here? Isn't this 1 sig fig? Should my answer just be 2? It's infinite. A balanced chemical equation is based on counting. So any numbers you take from a balanced chemical equation will always be infinitely significant, which means our answer would be a 2 sig figs, which it is. Now, before we get going, I kind of want to draw a little roadmap here. And this may seem weird at first, but this is a little thing I do, and we're going to come back to it all the time, which is, we said that if you know how many moles of something you have, and we said that we use the letter N to signify how many moles you have, from that, we can actually figure out some stuff. If we wanted to, we could actually figure out how many particles that is. Now, that's a big stupid waste of time. We never actually do it. We did it in like one lesson, and we'll probably never do it again. There'll probably be one test question just because I feel like I'm supposed to ask you. But having said that, that's easy to do because how many particles are in a mole? We can always say 1 mole is equal to 6.02 times 10 to the 23rd of anything, right? So that's easy math to do, right? If I told you we have 1 mole, you could say, oh, That's 6.02 times 10 to the 23rd particles, right? And if I told you have 3 moles, you could just quickly multiply that number by 3, and you'd tell me that's how many particles we have, right? If I told you I had 10 moles, it'd be 6.02 times 10 to the 24, et cetera, et cetera. Does that feel fine? We did a whole lesson on that. Then we did another whole day where we said, okay, if you know how many moles of something you have, the whole point of that is that now we can work in grams, right? And if we know how many moles of something we have, we can tell how many grams it is, because on the periodic table, it tells us how much a mole of every element weighs. How much does a mole of carbon weigh? 12.011. Beautiful. 12.011 grams is 1 mole. How much does a mole of nickel weigh? Very good. 58. Right? So all we have to do here is look at the periodic table, and it can tell us how many grams something is. This, by the way, not for nothing. If I told you that you have 1.5 times 10 to the 24 particles, how much does it weigh? Well, first you could go from how many particles it is to how many moles it is, and then you could go from how many moles it is to how many grams it is. So we could start to kind of take this journey. But today, we learned a new thing, which is that if we're talking in an equation, if you know how many moles of A were involved in the equation, then you can figure out how many moles of a different thing, how many moles of B, if we wanted to, are involved in the equation. Does that make sense? Like if we wanted to, we could say, well, wait a minute, if we have 4 moles of hydrogen, that means I'm just doubling the recipe. How many moles of oxygen will I get if I double this recipe? 2. So we can also do that. So we're going to start to build this little kind of roadmap. And of course, once we know how many moles of B, if we wanted to, we could figure out how many grams of B that is. And if we really wanted to, though I don't know why we would, we could figure out how many number of particles of B we have. Though again, who cares? And this change happens by looking at the balanced equation. Now, at first, you may find this diagram to be kind of weird or stupid, but actually, you're going to see me use it constantly because I find it really easy to navigate. This can help you make a roadmap for a question. If I give you this and ask you to tell me that, you can just say like, well, okay, we start here. Can I get there directly? No, but I could turn grams of A into moles of A, and I could turn moles of A into moles of B, and I could turn moles of B into grams of B. So this little kind of roadmap for questions, I have found to be a really powerful tool. That's not anything like life-alteringly fancy, but it just kind of is a reminder of what we can do and what we can't. So let's try another question. And if we need to, we'll refer back to this. How many moles of oxygen gas are produced if 3.4 times 10 to the 3 grams of lithium oxide are decomposed? So here we're going from moles of one thing to grams of a different thing, or actually vice versa. Does that make sense? We are starting with what? What's the starting information we know? Yeah, grams of lithium. Absolutely. So the mass of lithium, which is 3.4 times 10 to the 3 grams of lithium, right? That's what we're starting with. And what do we want to end up with? So we're starting with moles of lithium, or grams of lithium rather. And what does it want us to end up with? Moles of oxygen. So we're going to have to do some math here, right? We're going to have to know how many moles of oxygen gas we have. And to do that, this is where I said it's kind of helpful to make a little roadmap. I need to go from grams of one thing, in this case, grams of, it was lithium, right? Okay. And I want to go from grams of lithium to moles of something else. In this case, we can say moles, was it oxygen? Yeah. How am I going to go from grams of one thing to moles of something else? Well, do you see here we can get a roadmap? We're going to go from grams of lithium to moles of lithium. And how will we do that? We'll look at the periodic table because it tells us how many grams are in a mole of something, right? You could look right now and tell me how many grams are in a mole of lithium. 6.941. Good. Once we've gone from grams of lithium and now we're talking about moles of lithium, what can I do next? Yeah.
It says lithium oxide.
Okay, lithium oxide. There we go. And then, once we know how many moles of lithium oxide we have, what can we do then? If I know how many moles I have here, the next thing I can do is I can look and say, well, now I know how many moles of oxygen. And what am I going to have to look at for that? A balanced equation. So that's going to be our roadmap. We can use the periodic table to say, well, if I know how many moles or grams of lithium oxide I have, I can determine how many moles that is. And then I can say, once I know how many moles of lithium oxide I have, I can just look at the recipe and it'll tell me how much oxygen that's going to relate to. Does that kind of make sense? We take our mass and turn it into a counting number because reactions are done by counting. And then we look at the recipe to count, say if I have this many of one thing, I'll have this many of another. That's the whole thing. Grams to moles, because we want to do chemistry, and we do chemistry on paper with counting. Then we can just answer our question. But we had to start in grams, because even though we do chemistry on paper by counting, we do chemistry in the lab by weighing stuff out and measuring stuff. Let's actually try it. By the way, what am I going to need to know? Well, I'm going to need to know on the periodic table how much lithium oxide weighs, and I'm also going to need to know on the from the equation what the balanced chemical equation is. So we got some work to do. Shall we give it a try? What we're going to try here then is we're going to go from lithium oxide all the way up to oxygen. Now, we need a balanced equation. And this is a decomposition reaction. And what are we decomposing? Lithium oxide. This is straight unit 2. What's lithium oxide? Can I assume it's LiO? No. In fact, what I need to do is say lithium wants to give away how many electrons? How many? 1. Which means that a single lithium would give away 1 electron. 2 of them would give away 3 of them would give away 3. Okay. What about oxygen? How many does it want to receive? So, they balance out here. How many lithiums, how many oxygens? 2 lithiums, 1 oxygen. So Li2O. When it decomposes, by the way, this is an ionic compound, so it should be a solid, liquid, or gas. What do we think? Nobody's given me a confident answer yet. Yeah, this would be a solid. It could be aqueous. Lithium oxide will definitely dissolve in water, I think. But if we're doing a decomposition reaction, would we want to dissolve it in water? Probably not, right? We're probably going to want to heat it up, right? So probably work with it as a solid. What's it going to break down into? Lithium and oxygen. And then just a 2 there, and we're balanced, and we're good to go. Pretty sure it is. Because we have 2 lithiums here, 2 lithiums there, 1 oxygen there, 1 oxygen there, and we're good. And obviously that'll be a solid, and this will presumably be a gas. Oxygen's diatomic. Darn it. So that's not O, it's O2, which means I have to balance this out. Yeah, that looks good. How's that feel? Not too bad? Now this is actually good because it tells us however many moles of lithium oxide I have, how many moles of oxygen will I get? 1. For every 2 moles of lithium oxide, I only get 1 mole of oxygen, right? That's the recipe. How many moles of lithium do I get? 4. Do we see that? So now let's remind ourselves. We are starting by knowing the mass of lithium oxide. And we want to end up knowing how many moles of oxygen we have. Now again, chemistry, chemical reactions aren't done with grams. They are done with moles. This recipe does not say that 2 grams of lithium oxide will break down to give you 4 grams of lithium and 1 gram of oxygen. First of all, that wouldn't even make sense. Can 2 grams magically turn into 5 grams? No. This says that 2 molecules, in this case formula units, break down into 4 atoms and 1 molecule. So you have to work with counting, which means we can't do chemistry in grams, we have to do chemistry in moles. So grams of lithium oxide is going to get converted to moles of lithium oxide. And where would we look to do that? What tells us how much a mole of something weighs? The periodic table. So if we just look at the periodic table, it will tell us how much that weighs. And then when we want to go from moles of one thing to moles of something else, now we're doing chemistry. Now we're doing stoichiometry. Where do we look? The equation, because the equation tells us that however many moles of lithium oxide we have, for every 2 of those, we're only going to get 1 oxygen. That's the recipe. So for this, we look at the balanced equation. Now, I have this information. Have I gone to the periodic table and figured out how many grams are in a mole of lithium oxide yet? Should we just go ahead and do that now so we know it? I think so. So if we want to know how much a mole of lithium oxide weighs, we're going to have to look at lithium, and we're going to have to look at oxygen. But how many lithiums do I have in lithium oxide? 2. Right. So let's do this. How much does a mole of lithium weigh? 6.941. And what's the unit? It is, but we're never going to work with that again because now we're doing stoichiometry, which means we want to put this on the bench, which means it's also true that there's 6.941 grams of lithium oxide in a mole, or of lithium rather. And what about oxygen? Yeah, very good. And if we can do that in our head, 14 plus 16, this should be roughly 30. It's going to be less than 30. It's going to be 29 point. What is it? Great. 29.8814. And yeah, we only can actually support how many decimal places here? 3 decimal places there. Yep, which means that 4 has to go. By the way, if you kept it, it's not going to matter because we have way more sig figs here than we have in the other. But Angela's entirely right. We should round it thusly. Okay, now, that's just setting the table. Now we can do today's actual lesson. See all the information we need to get before we can actually do a question? So if you think about this, to do this question, first of all, we had to figure out what lithium oxide was. So we had to go to Unit 1, we had to figure out the formula for lithium oxide. Then we're told it decomposes, which means we need to go back to Unit 2 and say, well, what's a decomposition reaction? Oh, right, it splits apart, balance it. Unit 1 and Unit 2, right? Then we can start Unit 3 and say, well, okay, I need to know how much everything weighs. Lithium oxide, I can figure out how much it weighs just looking at the periodic table. I'm not going to bother with doing this for lithium because that's just right on the periodic table. And likewise, oxygen, if we need its mass, it's just 15.994 times 2, right? We could write that down too if we want. This is all just setting the table. This is all just getting mise en place. As a great band would say, everything in its right place. Now that everything's in its right place, we can actually do the chemistry, which is pretty trivial. We're going to say, okay, I've started off with grams of lithium oxide, but I don't want to know about grams of lithium oxide. I want to know about moles of oxygen. Can I jump from grams of one thing to moles of something else directly? No. But I can say from grams to moles quite easily. All I have to do is look at the periodic table. And then if I have a balanced equation, I can say, well, if I have this many moles of this thing, I know how many moles of the other thing I will get. So we're going to have to do this not in 1 step, but in 2 steps. You'll get to questions eventually where there's 17 steps. But by then we're going to be so good at this you won't even think about it. Right now, 2 steps is a new challenge, right? It's the first time we've done that. So let's get to try it again. And you see, again, you don't have to draw a little roadmap. I draw a little roadmap for every question. That's what I kind of call this. This is my plan of attack, how I'm going to attach it. And I do that by kind of looking at this little map here that tells me how we can go from one thing to another. You may not find that useful, but I think with a bit of practice, most students find that this is useful. So now we can do this. We can say we started off having how many grams of lithium oxide? This question really would have gone better for me if I'd also highlighted the word oxide in that title. There we go. How many grams of lithium oxide do we start with? 3.4 times 10 to the 3 grams of lithium oxide. And then we would say we multiply by a fraction. And what don't I want to talk about? So where am I going to put that? On the bottom. Now, what I would like to do is just put moles of O2 up here. But can I make that jump? Is there any way to know how many grams of one thing gives me moles of a different thing? No, so I'm only able to do a first step, which is I can go from grams of lithium oxide to moles of lithium oxide. Right? And then I need to put a number in here. Well, how many moles in a gram of lithium oxide, or how many grams in a mole of lithium oxide? What number can go here? And if you can't remember, where do we look to know how many grams are in a mole of something? Periodic table. And we've already done it. Right? We've already done this math. And this math tells us what number goes here? Great. And is that going to go on the top or on the bottom? Yeah, because there's 29.8881 grams in how many moles? What does the periodic table always tell us? The periodic table doesn't know what question you're doing, so it never changes. It always tells you how many grams are in 1 mole. Right? Good. Now, what units cancel here? Grams of lithium oxide. If I were to stop calculating now and punch this into my calculator, what would I know? Of moles of what? I'd know how many moles of lithium oxide I started off with. But that's not what the question asked me to find. So we're going to keep going. We're not going to stop here, calculate it, and then start again. We're just going to keep going. We're going to make a multiplication sign, and we're just going to do this again. Another fraction. Because what don't I want to talk about now? Moles of what? Yeah, because that's not what the question asked me. What did the question ask me? Moles of oxygen. And now, is it possible to find this information? When we want to relate moles of one thing to moles of another thing, what do we have to look at? Yeah, very good. The balanced chemical equation. That sounds like, I didn't mean that to sound sarcastic. That is good. It's your first time doing this. Let's look at the balanced equation. In the balanced equation, how many moles of oxygen are present? Yeah, 1 mole of oxygen in that balanced chemical equation. How many moles of lithium oxide in the balanced chemical equation? 2. And now, what units cancel? Moles of lithium oxide. So the unit that remains is moles of oxygen. So the math trick works for us. We've canceled grams, we've canceled moles of lithium oxide, we're left with moles of oxygen. So as long as all of the information we put into the equation is true, we're going to get a true answer. So let's quickly review. Did we start with 3.4 times 10 to the 3 grams of lithium oxide? Yeah, the question told me that. Is it true that every 29.881 grams is 1 mole? Well, yeah. How do we get that information? Periodic table. Is it true that when these things react, it takes 2 moles of lithium oxide to get 1 mole of oxygen? Yeah, how do we find that information? Balanced chemical equation. So the units cancel, and all the information is true. So if we do this math, it's going to answer the question for us. And now we can just do this. And what is it? That's 3,400 divided by 30. So that's going to be roughly 100, half of that. This is going to be a little bit bigger than 50, maybe 54, 55. What is it? 56.89, great. But I'll show you guys the math up here just to make sure we all know how we'd punch this into our calculator. We are going to say 3.4 times 10 to the 3. Make sure you're using your scientific notation button. And if you don't know how to use your scientific notation button, talk to me. We don't want to type this in as 3.4 times 10 to the exponent 3. It'll work, but it's going to make problems for you when you get to more complicated ones, and anytime you divide by scientific notation, you're going to screw it up. So just learn how to use your scientific notation button. EXP, that's right. On the yellow calculators, it's second function comma, but your calculator may vary. Just ask me. And then what are we doing? 3.4 times 10 to the 3 times 1 divided by, good, times divided by, and we get 56.8923. And then, how many sig figs do we have to work with here? How many sig figs here? How many here? Infinite, good. How many sig figs here? 5. How many sig figs here? Infinite. Here? Infinite. That looks like a fish. That still kind of looks like a fish. In fact, there you go. Happy little fish sig figs. So, how many sig figs in my answer? 2. Because that's the lowest of 2, 5, and infinity. So, this answer can only be to here. And is this closer to being 56 or 57? 57. Good. So we would say 57. And what's our unit again? Moles of oxygen. Okay. That is a really, really, really sophisticated piece of science we just did. Right? Can we all agree there's a lot going on in that question? Right? Like a lot. There is a lot of a lot of a lot. This is the entire course up to today, minus I guess, isotopes. But other than the topic of isotopes, everything we've done in this course so far has been in this one question, right? You had to find a formula for lithium oxide. You had to balance a chemical equation for its decomposition. You had to figure out the molar mass of everything involved. And then you had to do stoichiometry to figure out, given a mass of one thing, how much of something else would be produced. This is really hard. We are going to stop after this lesson and just spend days practicing this. And we're going to do a lab where we practice this. It's going to take some time because this is going to take practice. All right? It's hard. This is tricky stuff. Yes, my friend? Oh, they will. Don't worry. But not in this course. But don't worry. Yeah. But I mean, that's actually the... Once you get at this, that won't scare you at all. You're like, oh, there's 2 answers, big deal. Right? All right, so listen, if this feels a little overwhelming, don't be discouraged. Do you know why it feels a little overwhelming? Because it's a lot. It's a lot of stuff. Right? It's just a big topic. So don't be overwhelmed by this. Don't be stressed out by it, but also don't try to ignore it away because we're going to do this over and over and over and over and over again. Next unit, you're going to go, oh, wow. We've introduced a new topic, but the stoichiometry is not going anywhere. So, let's try another one, shall we? All right. Exempla gratia 3. If 3.2 grams of solid copper were to react with excess oxygen. What do I mean by excess? What's it mean to something to be in excess? Yeah, a lot. More than you need. All right? In other words, all the oxygen in the world, all the oxygen you need. If 3.2 grams of solid copper were to react with excess oxygen, how many grams of whatever metal oxide is produced would be produced? Now, to make life easy for this question, we're going to assume that we get copper 2 oxide. That was the black one we got, remember? And we got more of that than we did, the red. Does that make sense? So we're not going to work with both here. That would be really... so we'll say here that you can assume that copper 2 oxide is produced. Otherwise, this question would be a complete pain in the butt. I don't want to be a complete pain in the butt. Not yet. I'll get there. Angela, you cut me to the quick. That's why you're going to get the extra special hard exam on red paper. How'd that feel if everyone else got their exam was just on white paper and then yours was on like a deep crimson red and it said extra hard on the cover in big all caps letters?
If it was like extra hard, I just like leave it there. I'm like, yeah, I'm not doing that. I like make them talk to my mom.
That's
like,
easy to grade. Your mom would be on my side.
I was like, hire a lawyer and be like, this is not good.
Your mom would be like, what? You're afraid of hard questions? Coward? Sorry? Blue ink. Blue ink. Okay. I actually don't write on exams when I mark them because you guys don't get them back. I just mark them directly into my computer. Like it's not like a test where you hand it back, right? So I mark it right into my computer. Anyway, but you don't get them back. You can come look at them. Like I've got all the last semester exams there that I really do need to go put in the vault. So they're available for you. But I always just print out my marking template after that and staple it to the top of them and go. Yeah, you can see them. That's right, yeah.
That's how we learn that. How do like, oh yeah, I get
Do you understand the exam comes at the end of the course when you're supposed to have already learned and now I'm evaluating your learning? The exam is not a tool for the exam is not a tool for your learning. The exam is finally that moment where I get to see whether your learning and my teaching has been effective, yay, or ineffective, boo. And for the record, with this group of people here, overwhelmingly effective. You guys are very clever, capable people, and you make me feel good about myself. But anyway, so let's get to work. Not that it has anything to do with me, but that's fine. I'm here along for the ride. This is something I believe as a teacher deeply, which is when your kids are successful and thriving, that really has nothing to do with you. That just means the kids you teach are smart. On the other hand, when your kids are failing miserably, that's your fault because it's your job to teach them. I have a fully, you can only be the problem approach to being a teacher. Anyway, all right, how do we approach this question? There's a lot going on here. We're given grams of one thing, and we want to know how many grams of something else are going to come out the other side. Right? That's what this asks here. How do we do that? What are we going to need? Well, if you look here, this is where I find my little roadmap helpful. If I say I'm starting with grams of copper, and I want to know how many grams of copper oxide, I'm going from the mass of one thing to the mass of something else. Can I make that journey directly? No, there's no information there. So what am I going to have to do? First, we don't do chemistry with grams. We do chemistry with moles. So to do the actual chemistry, we're going to have to convert grams to moles. Where are we going to look to get the information we need to do that? Periodic table. Once I've done that, we can actually do some chemistry. We can do some stoichiometry. And I can go from one thing to another. I just have to look at the balanced chemical equation, right? And then I'll know how many moles of something else I have, but I don't weigh things out and see how I did in the real world with how many moles there are. That's a counting unit. To get back into the real world, I have to work in grams. And how do I go from moles to grams? I look again at the periodic table. So this is our roadmap. Grams to moles, moles of one thing to moles of something else, moles back into grams. So this is going to be a 3-step, right? Now, that's the first thing I'd like to write here. I like to make my little roadmap. You don't have to do this. There's no grade specifically for this, though if you get the question wrong, but you made me a roadmap, at least you'll get some credit for that. We're going to go from grams of copper to moles of copper. And then once I've gone from moles of copper, we can go to moles of copper oxide, whatever that is. We don't even have the formula yet. And then from moles of copper oxide, I can go to grams of copper oxide. And that's my roadmap. And again, when I want to go from grams to moles, where do I get the information to do that? Grams to moles, where's that information stored? Periodic table is right. Very good. And then when I want to go from moles of one thing to moles of something else, an actual chemical reaction, where do we look for that information? It is the balanced equation. Good. And then again, when I want to go from moles back to grams, where am I going to look for that information? On the periodic table. Okay. Now, let's get the information we need. And the first piece of information we're going to need is a balanced chemical equation. So let's do that. We can say that we're starting off with what? Copper in its solid form. And we're reacting it with oxygen. You happy with that? It's diatomic. Okay. What's its state of matter? It's a gas. All right. Now, I told you that we can assume that the product will be what? Copper 2 oxide. So in that case, copper is giving away how many electrons? 2. Oxygen wants to take how many electrons? That one's actually nice. What's the formula? All right. CuO. And is that a balanced equation? How do we balance it? How do we balance it? Yeah. In front of what? Yeah, beautiful. Very good. Excellent. So there we go. We have our balanced chemical equation, right? And then to continue to set the table, to continue to be mise en place, to continue to have everything in its right place. I will not infringe upon our relationship by singing to you.
No, it was great.
Yeah.
It was amazing.
I'll get my keyboard.
Yeah.
It's a great keyboard riff. Anyway, before we want to get going, how much does a mole of copper weigh? We're going to need that information. How much does a mole of copper weigh? Because we're going to use that here, right? We're going to have to know how many grams per mole there are for copper. How much? Yeah, 63.546 grams of copper in a mole of copper, right? You don't actually have to write the Cu in that, but I just did. Okay, that's the easy one. But what else are we going to have to go from grams and moles? Not just copper, but also copper oxide. That one's slightly more annoying, but not a big deal. How much does a mole of copper weigh again? 63.546 grams in a mole. And how much does oxygen weigh? 15.9994 grams in a mole, which means that copper 2 oxide would be how much? That's going to be 79.545. And we're going to have to stop at that 5 because 3 sig figs, or 3 decimal places rather, not sig figs. So there we go. All of that just to get ready to do stoichiometry. Does that make sense? We haven't done any stoichiometry yet. We've just given ourselves the information we need. Now, could I have started doing math and just figured out each of these things as I needed them? I could have. I like to have all the information ready and available to me. In my experience, that makes me make fewer errors. Again, mise en place. I managed a restaurant, so I scream and yell at people about being mise en place, being ready to go. When I managed a sports bar, we called it being game ready. But I was still just screaming at people about being mise en place, right? Which is to say, like, you want to be ready to go. There's nothing, I don't know about you, when I go to a restaurant and they drop my food off but I don't have cutlery yet, I'm so irritated. I get so mad. I think I don't take it out on anyone. I don't like throw a fit or anything. I just live with it. But on the inside, the restaurant manager in me is like, who is running this place? Like, why doesn't the server know how to do the job properly? And then, like, if they come to the table and they're like, who's having the chicken? I'm like, I don't know. Aren't you getting paid to know who's getting the chicken? And again, I'm not mad at the server. I'm always mad at the person running the place, right? Like, why don't you make your people do their job right? You know? Staff will do a good job if you make them. Likewise, when you're doing chemistry, have the cutlery on the table. The water glass there, have a straw, have a teaspoon, all the stuff you need right there on the table. See here? This is a nicely set table. Somebody needs a napkin, they shouldn't have to ask you for a napkin, but you want to have wing sauce all over your hands and like your mouth's dirty and be like, I have a napkin. Great. And now I got to find a waitress and be like, hey, waitress, as you're waving with your saucy hand going, can you come over and give me, you just want to have it on the table. See here? Everything ready to go. Now we can do some chemistry. And my advice is always reread the question one last time once you're ready to actually do some chemistry. The chemistry says we're starting with 3.2 grams of this, and we want to know how many grams of that do we get. It's easy to forget how easy that actually is as a concept because we've just done all this crap. We've written all this stuff down. But really we're saying, if I start with some of this, how much of this am I going to get? Does that make sense? And now we can just lay it out. Let's do some dimensional analysis. This one's going to take 3 steps, but we're ready. How many grams of copper do we start with? 3.2 grams of copper. So let's begin. We have 3.2 grams of copper to start off with. And we're going to do dimensional analysis, which means we're going to multiply by a fraction. I don't want to talk about grams of copper. Really, I want to talk about grams of copper oxide, but I can't do that directly. So I want to cancel grams of copper. Where am I going to put it? And instead, for my first step, we're going to go from grams of copper to, where's that going to go? On the top. Now I need a number for that, but luckily I've already got it. How much does a mole of copper weigh? Great. So do I want to do this? Do I want to do that? No, because that says 63.546 moles of copper. But the periodic table doesn't tell me the weight of 63.546 moles of copper. It tells me the weight of 1 mole of copper. And it tells me that that mole of copper weighs 63.546 grams. What units cancel here? What units cancel? Grams of copper. If I were to plug this into my calculator, if I stopped calculating now, what would I know? Moles of what? No, moles of what? Copper. I'd know how many moles of copper I have, right? You can do the math, but that's not what I want to know. So I'm going to keep going. When I say I'm going to keep going, what am I going to do? Yep. So literally, physically on the page, what am I going to do? You're totally right. Yeah, I'm going to multiply it by another fraction. Good. And now, you're totally right. What do I want to get rid of now? Great. Where am I going to put it? On the bottom. What do I want to talk about now? Well, from moles of copper, we can go to moles of... if I wanted to, absolutely, 100%. But the question doesn't ask about oxygen. It asks about copper oxide. So, I'm going to go from moles of copper to moles of copper oxide, right? And what is that relationship? From the balanced chemical equation, in the recipe, how many moles of copper do we use? 2. So let's put it there. How many moles of copper oxide do we produce? 2. So let's put it there. What units cancel? So if I were to stop calculating now, what would I know? If I did all this math, I would know how many moles of copper oxide were produced. Good. Which is fine, except the question didn't ask me to tell you how many moles were produced. It asked you to tell me how many grams were produced. So we're going to do our last step, and we're going to say, okay, what don't I want to talk about now? Moles of copper oxide. Where should I put that? On the bottom. That math trick works. That's going to cancel. What do I want to talk about? Grams of copper oxide. So by the math, that's going to now tell me how many grams we have, because moles of copper oxide is going to cancel. But I need a number to put in here. Where do I find that number? Periodic table, and we've already done it. How much does a mole of copper oxide weigh? How much does a mole of copper oxide weigh? Great, and where did we get that information again? From the periodic table. And now, when I do this calculation, I'm going to know how many grams of copper oxide were produced when we reacted 3.2 grams of copper. Yeah? Sorry? No, because we got this information from where? Does the periodic table know that in this particular reaction we used 2 moles of copper oxide? No. This information isn't, because 2 moles of copper oxide don't weigh 79.54 grams. Does that make sense? 1 mole of copper oxide weighs that much. So each fraction has to be internally true. It has to be true to itself. This fraction is internally true. 1 mole of copper oxide weighs 79.545 grams. This fraction is true. In this reaction, 2 moles of copper oxide are yielded from 2 moles of copper. And this fraction is internally true. From the periodic table, we know 1 mole of copper weighs 63.545 grams. That's a great question, by the way. It's the most common mistake people make, where they take this number and put it down here again. That's the mistake everyone wants to make. It's natural. I promise you're going to make that mistake at some point. But don't ever forget, the periodic table doesn't know what question you're doing. So when you use the periodic table to say how much a mole of something weighs, it doesn't know that in the equation you're doing, you're actually using 5 moles. This information comes from the periodic table, so it's the mass of 1 mole. Did that answer your question? Good. And again, don't feel bad when you make that mistake. Every one of you is going to make that mistake at some point. I still make it every once in a while. You're just not thinking and you're like, ooh, I have 3 moles, right? But the periodic table doesn't know that. It tells you the weight of 1 mole. Yes?
So then you take 1 mole and then multiply it by 3.
You could do that. Yeah, that would be messier, but you absolutely could do it. And like I've seen people do that, where they'll change this to 2 and then double that number. That's like unnecessary. It might even be confusing, but if it gets you there, it's not wrong. So yeah, you could. That's actually a really good insight. As long as the ratio is true, you're good. As long as every fraction in here is true, you will get the right answer. So if you put the mass of 2 moles in here, that's great. Nothing wrong with that. Not how I would recommend doing it, because you're doing unnecessary math, but it will work. So yeah, if you would put a 2 down here, Snana, and then you had doubled this so that it was 159.90, or 0.090, like that'd be great. Go nuts. But easier just to do it this way. Now, if we do this math, 3.2 divided by 6.3, that's going to be like 0.05-ish. Then we're basically multiplying that by 1, and then we're multiplying it by that. So this is going to be on the order of 4. Like we're talking like 4.1, 4.2-ish. Is it 4.0? Okay. So what answer do we actually get? 4.0 what? 4.0056. Okay, blah, 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 blah. And then obviously sig figs. How many sig figs here? 2. And good job. You guys obviously knew the right number to go with. Here we have 5 sig figs, right? Also known as S sig figs, apparently. How many sig figs here? Infinite. How many here? Infinite. How many here? Infinite. How many here? How many here? 5. And so the answer has to be to how many sig figs? 2. And so 4.00, is that closer to 4.0 or 4.1? Obviously 4.0. And what's the unit? Grams of copper oxide. Cool. Now again, that's sophisticated math. We have just, like it's sophisticated math, but it's sophisticated everything. This is really integrated, right? Like it's using a lot of skills. It's probably, there's not a lot of times in your kind of math science career thus far, you've probably had to put like 3 units worth of stuff together in a single question. You know what I mean? And you're going to do that for every question. That is where the middle of this course can start to feel a little discouraging for people. In the end, this is going to be a feature, not a bug, because it gives you so much practice. Like I said, the great advantage here is you don't have to go back and study Unit 1 in June and be like, oh my God, what was Unit 1? I don't remember any of this, because you're doing it every day. You're not going to have to go back and study Unit 2 in June, because you're going to be doing it every day. But right now in this moment, this can feel a little bit like, whoa, this is a lot of things that goes into doing one question, right? I think even more so than physics or even more so than math, this draws on like multiple units and you have to like coalesce it all together. You have to put your skills together. But the flip side is this. In the end, once you get it, it becomes intuitive. I had a high school chemistry teacher who always referred to things as intuitively obvious. And as we were all sitting there absolutely not understanding what he was talking about, I found it really offensive when he would say that things were intuitively obvious. This isn't intuitively obvious at all. It's not at all obvious. It takes work. But what it is the more you do it, the more you will develop an intuition for it. The more it will start to feel natural. This thing here where we talked through the dimensional analysis, you guys are already doing fantastic with. You really are. And I know it still feels shaky. It's supposed to feel shaky. It's a new skill. Remember when you first started to ride a bike? I don't know about you, but I used to fall over a lot. Also, I used to hit my neighbor's truck a lot, which looking back on it, I feel bad about it. At the time, I thought I was worried about my bike. Looking back, I probably should have been more worried about his truck. In my defense, I was like 5, right? How old are you when you learned to ride a bike? Like 5, 6?
8.
8? Never learned. Max, can we teach you how to ride a bike?
No.
Down the hall? Max, you'd be so cool if you were riding the bike down the hall. And then when you get in trouble, you can blame me. We'll talk.
Still get in trouble.
No, I'll get in trouble, and I'm totally at peace with that. Anyway, we'll talk. What does Mike say? I rode a bike down the hall the other week, and I felt so much joy.
Is it the one that's always in the last shot?
Yeah. Oh, I felt good. I felt powerful. Anyway, okay, listen up. Shh. There's a couple more practice questions on here. In fact, there's a bunch. We're going to take them all up tomorrow. Unlike sometimes where I do the whole, like, I want you to do your homework. We'll take these all up tomorrow, but I want you to try them all. Does that make sense? Try. It is perfectly okay if you don't get there yet. It's going to take some practice. Try all the homework questions, okay? So if you can make an effort to do all of the subsequent questions, tomorrow we'll take some practice and see how we get with them. How's today feeling? Somewhere, yeah. And that's okay. Like, gonna take some time. But listen, try. Do I have to sing that song? Oh, baby, you try.